Good morning, everyone. So today's lecture will be on 3D shape analysis and matching, a last lecture of computer vision. And after the lecture, we shall also have a discussion on exam. Okay, so we'll discuss some thing about the exam, and yes, a brief discussion about the project as well. So we'll just revise 3D shape acquisition techniques very briefly. We covered that in one of the previous lectures, and then we'll discuss how to represent 3D data. So the interesting thing is, in most of the computer vision lectures, or the courses, you won't find this 3D stuff, right? But the 3D is reality, right? So, and all the advanced techniques are now geared towards this 3D stuff. So that's the main purpose of including this 3D shape analysis and matching stuff here in this lecture. We should also look into applying 2D image techniques on 3D data. So you guys have done some filtering, some other image processing stuff, some computer vision stuff on 2D, like edge detection, corner detection. So we'll apply those 2D image techniques on 3D data. Then we'll discuss one of the famous algorithms of registration, which is iterative closest point. And we'll also discuss keypoint detection in 3D. So we discussed one of the techniques in 2D, which was Harris corner detector. And SIFT code itself also comes with a keypoint detector. So in 3D, we'll look at two different techniques. We'll discuss two different techniques. And then some 3D feature extraction and matching will be also part of discussion today. So starting with the acquisition techniques. So if you remember, we discussed laser, stripe, scanner. So what happens is stripe is moved over a 3D object. And that stripe actually covers or captures the image. So what happens that stripe is projected perpendicular to the epipolar line. And if you remember from that lecture, we have a correspondence problem. So if a line is projected perpendicular to an epipolar line, it will intersect with the epipolar line, and that will give us solution to the correspondence problem. That triangulation is tough. So we have one camera, one projector that forms a triangle. Right, we get that triangle, and that helps us to find, capture this surface. Now let's say if there are 1,000 points in this image here, how many times do you need to project this stripe? So going all the way from here to here, let's say 1,000 points that you need to, or 1,000 columns, then you need to scan it 1,000 times. You have to project that stripe 1,000 times. So you project it, you move it, you project it, you move it, you project it, right? So as such, this is a very slow process. Acquisition with this stripe, this laser stripe, is a very slow process. Now, so we have one such a scanner here in CSSE. It's an Ultra-Wavelet 3D scanner. And it has a resolution of 640 by 480 and 1 mm resolution. And the images that you see on your screen, these have been captured using that scanner. The first one especially is a UWA object data set, which was proposed back in 2005 or 6. Right? So all these images were captured using that Minolta scanner. And we have some phase images as well. And you can see these lasers are quite safe for the face scanning as well. No images, right? No problem with that. Even if you're, let's say, putting on these normal glasses, you can still capture the information about the underlying skin, even their sunglasses. So that laser can easily pass through your sunglasses as well. And it's very good for face recognition, even when your eyes are occluded or they're covered with something, right? So slow scanning, with a normal scanning, we get 640 by 480 image, and with fast scanning, we get 320 by 240 image, and it takes less than a second, right? Now, another type of techniques that we discussed was structured light. So, and Connect 1 actually works on this principle. So what happens, a random pattern is projected on a scene, and the depth information or the 3D information about the scene is captured, right? So let's say you try to capture this scene or try to extract 3D information from this scene using this stereo vision system. What will be the problem here? See, there are so many flat surfaces, some repetitive patterns there. So stereo vision would fail in that case, right? So instead of that, if you're just projecting some random patterns there, that will actually help you to identify the neighboring pixel and the difference between the neighboring pixels. And that's how the depth information is captured in this particular case. And if you guys remember, this Connect 1 actually came with Xbox 360, if I'm not wrong. Have you guys used Xbox 360? You've used that one? Oh, that's okay. So it came with that. So it captures 3D information, and if you remember, if you wave your hand and all that stuff, you can do so many things. Or 3D games, you can play 3D games in that with your Connect. Okay, so here are some example images. The first one is, of course, just RGB image. So Connect has one RGB camera. It has one depth camera, the infrared one. So the first image is just an RGB image. The second one is a depth map, right? The depth information is right there in that image. And the third one is the color information captured by Connect has been mapped on each pixel on depth image, right? Because if you look at the center image, the one in the middle, it doesn't carry much information. The shades are somewhat similar in so many objects, right? There's so many different places. So if you're using this information, if you use this information directly, you won't be able to make some good decision. Let's say if your aim is recognition, you won't be able to identify a computer or a chair in this image. But if you combine your 2D information with 3D information, that will make your task pretty simple. Then we have some comparison with other scanners. We have images captured with Minolta, Connect, and Inspect. And if you look at the second row, the depth images, okay, the color images are good actually, especially for the Connect. But if you look at the depth information, the 3D information is not that good for Connect. But for Minolta and other scanners, because they're high resolution scanners, information is good, you have very smooth surfaces. But in the case of Connect, we have some wavy shapes on image, which is not good, right? They're very problematic when you are doing some tasks like recognition or let's say segmentation, or you're trying to find some significant key points on the face or facial landmark detection. These sort of things are very problematic. But we will discuss how to smooth these images and how to make them smooth. Now, just an example. So how does Connect work? So it captures a scene with a frame rate of 30 frames per second, right? So what happens, either the scanner is a very lightweight scanner, you can hold it in your hand, right? So either the scanner is moved around the object, or you keep the scanner fixed and you rotate the object. And this is a 3D point cloud of a serial box, which has been captured using Connect. So we have 3D information plus color information all together in these images. And these images I got these images from Washington RGB dataset. And I believe we discussed this dataset just briefly. That's one of the largest low resolution datasets so far. They have 250,000 images of different objects, household objects. Okay, so once you have captured all these images from 360 degrees, what's next? You can integrate these views, you can register these views to get a complete 3D model of an object. And then that 3D model could be used for some graphical applications, some high sort of animations, and some recognition and all that stuff, right? So it's applicable for both computer vision and graphics, all that, right? And of course, you can get so many codes on OpenCV and MATLAB, and you can use your Kinect directly with that, right? And if you remember, in one of the lectures we discussed Kinect Fusion, which actually captures an image, aligns the images, fuses those images to construct a complete 3D scene, right? And now, after Kinect 1, I think in 2014, Kinect 2 was introduced. It is high resolution HD. It's, the RGB scanner is HD in that case. The depth scan is still the same, so it's not HD. And it works on the principle of time of flight. So what happens, the light is projected on an object, and the time that it takes, the reflection time it takes, like it strikes the object and returns to the scanner back, that information is used to capture an object in that particular case. And if you look at the image, it also calculates the difference between different facial expressions to that actually helps the scanner in determining that reflection time. So the difference of the expression also helps to evaluate that that thing actually. So compared to Kinect 1, it has a slightly better spatial resolution. That is, it captures more number of points. So if you have more number of points, that means it's good, like more information, right? So low resolution means you have lesser number of points, and you won't get a very good smooth 3D surface out of that. Now, once we have captured our data, whether it's we're using a high resolution Minolta scanner or a Kinect scanner, the next thing is representation of that 3D data, right? So raw 3D data is basically a collection of points called point cloud, and point cloud is a 3 by n matrix of the x, y, and z coordinate. It could be the other way around. It could be n by 3 matrix, right? So in case of n by 3 matrix, each column will represent 3 coordinates. The first column will be x, the second column will be y, and the third column will be z. In this representation 3 by n, the first row will be your x values, the second row will be your y values, and the third row will be your z values. Now this terminology point cloud is actually getting a lot of popularity, and we have there's a website with the name Point Cloud Library, right? And it deals with all the 3D point cloud stuff: visualization, acquisition, recognition, segmentation, detection. You'll find so many codes there. So point cloud is getting really popular these days. So a point cloud can be visualized using rendering software based on OpenGL. MATLAB has very good visualization system as well. You can find some good free-to-use software online for visualizing your 3D data. MeshLab, Scan, Analyze are two open source software that you can use. Now point clouds are then converted to mesh by connecting nearest points to form triangles or polygons. We have an example in the next few slides, and you'll see how those triangles are formed and how that mesh is formed here.
What happens if it's the closest, like there are two really close points, but they're not actually supposed to be connected together by a mesh?
Two closest points, and they're not.
So there might be a case where, like, you've got two objects that are really close together, but they're not touching.
Mm-hmm.
And then the points will be so close to each other that the mesh created will have them touching.
So what happens in that case? Each point cloud is treated as a separate data in that particular case. So when you form a mesh, and even when two objects are very close, each point cloud is treated as a separate data, another one is treated as separate data. You form your mesh. And then coming to the closest point, let's say if 2 points are very close to each other, they're in the overlapping region of two different surfaces, then yes, that information is mostly used for registration. You find the closest point, or closest corresponding points, and use that information to register the surfaces. Yeah?
Isn't that also down to the resolution of the scanner as well?
Yes, it has. So high resolution means more points and better surface, and low resolution means less point and a slightly wavy sort of surface, right? Now, polygons are filled and shaded to render surfaces. We have, in the next few slides, we'll see how that's done. And in MATLAB, it's pretty simple, right? It's a few steps, and Okay, so we have laser time of flight scanner here in UWA, and you guys are well familiar with this building, right? So it was captured using that time of flight scanner, and fortunately it works really well in the outdoor scenes. With the Kinect 1, it doesn't work really well actually. If you take it in the outdoor environments, it doesn't really work well. It's suitable for indoor scenes, but with the latest scanners, yes, you can use them outdoor and you can scan some 3D things. Okay, so we have a point cloud representation. You connect the nearest points to get a 3D mesh, the one which is shown in the center, and then you use surface rendering sort of techniques to get a complete 3D surface of an object or complete 3D model. Now, how this is done in MATLAB, so most of the scanners capture the images in the PLY format, PLY format, right? And the PLY file readers are available online. You can find and use any one of them. There are plenty of them available online, and you'll find the code is written in MATLAB. So you read the file, they give you a mesh, then you, from the mesh dot vertex, so mesh is a structure basically, so you have information about the triangles of the mesh, you have information about the vertices, vertex is the 3D point, right? And then you have information about the surface normals as well. So you extract x, y, and z values from the mesh using the vertices, and plot3 is the command that we use to plot the 3D point cloud, right? And axis equal just equalizes all the axes, and rotate 3D helps you to rotate the images. And then there is another command, try mesh, that actually connects all the nearest neighboring 3D points, and that helps you to, that gives you this sort of 3D mesh. And finally, you can actually fill in the information. There's another command, try surf, that you can use. So there's another command, try surf, which actually helps you to fill in the information in that mesh that has been formed, and with little steps like shading, interpolation, and color map, you can get a complete 3D surface out of that object, right? You can create a 3D surface. Now, as we don't have MATLAB here, I have just tried to create a small demo here for you guys. I hope, okay, so so again, instead of using read ply file, all that, what I have done, I have read all the 3 different sort of meshes for you guys, and I have saved them here in the 3D data, right? All this code and everything is available on LMS. If you go to lecture 12, you can find this material. So if you run this code, you will get, so the first one is plot 3, so you'll get this 3D sort of information, a complete 3D point cloud of an object, right? And each point represents x, y, and z information about that surface. Now, next thing is try mesh command. You can use try mesh, evaluate that, and it will give you a 3D mesh of an object. As we have a high resolution image, we have so many points, so we have some tiny, tiny triangles there. So if you just zoom into this image, you will find a 3D mesh or triangles of some small triangles on a 3D mesh, right? And finally, we have this try mesh that gives you a complete 3D model of an object, a very smooth surface of an object, right? So okay. Now, with now when we capture object from different views, right? From 360, we have 360 degrees, and we capture object from different angles. Now, what are the problems there? So a scanner can see a part of the object, right? If you're looking at an object, you can see it from here only. You don't have any information about the other side of this object. So what do we call it? In the literature, we have single view scan is actually referred to as 2.5D view in the literature, right? So when you capture an object using a depth camera, a 3D scanner, the view is called a 2.5D views. Why it's 2.5D views? Why it's not 2D? And why it's 2.5D? It's not 2D because you have the depth information in that, right? That's why you call it 2.5D. And why it's not 3D? Yes, it's not the complete model of an object. It's just one view of an object, right? So, and yes, Kinect, of course, strictly speaking, Kinect, one frame of this Kinect is a 2.5D, right? Because there are depth information and 2D information as well. So what's the solution? Scan the object multiple times from different angles and integrate those views, right? So before we can integrate scans, we need to register and align them. So when you capture an object from different viewpoints, let's say if you're moving the scanner, your coordinate axis is changing. Your like 0, 0 position is changing every time. You change that position, right? So there is some sort of translation and rotation in the object. Even if you're keeping your camera fixed and you're rotating an object, there is slight, what do you call it, like some sort of different appears in each view of the object with respect to the reference coordinate, because you're rotating the object in that particular case. So there is some sort of rotation and translation, and you need to calculate that before registering a 3D object, right? Or different 2.5D views of the object to get a 3D model. Now, for registration, we'll discuss one of the popular algorithms, ICP. And given 2 point clouds, P1 and P2, and we want to rotate and translate P2 so that it aligns with P1. That's our aim. So given 2 different point clouds, our aim is to align those views to register them. Now for each point in P2, find its nearest neighboring point in P1, and that nearest neighboring point is the corresponding point, right? So corresponding point you can either find by manual clicking. Okay, we have a point here on this view. You select exactly the same location on the other view, another view, right? And you do the same for both the images. And you need at least 3 points to do this registration. Then there are automatic ways of doing as well. You can do keypoint detection, feature extraction. You match the features, find the corresponding points, and then use those corresponding points to align your views, calculate rotation and translation matrices and all that. Now, once you have some information about the correspondence view, you remove incompatible points based on the distance. So let's say if corresponding point is far away, right? And you have a distance threshold, it's more than that, you just reject that, you drop that point. And then color information, let's say if you have some color information is available as well, and you find 2 corresponding points, color information doesn't change, right? And then you match the colors, and if the colors don't match, you just drop that point as well. And then you can compare surface normals, curvatures, and point boundaries as well, right? And based on all these, you can make a decision whether these points are corresponding or not. Okay, then what happens in ICP? You take all the corresponding points from P1 and P2. Of course, and we call that Y for surface P2, and we call that X for surface or point cloud P1. That's a subset of the points from P1 and P2, right? And so Y and X are the remaining set of corresponding points. And what is our aim? Our aim is to minimize this cost function, R times Y plus T minus X, where R is the rotation matrix and T is the translation vector. You multiply it with, you rotate and translate your Y to align it with X, and then you subtract your final matrix from X. And that's your cost function that you try to reduce. So find correspondences. So how does this algorithm works? You find correspondences between X and Y, and then you subtract mean of y from y and mean of x data from x, that means you're relocating or centering your data on its mean. You're centering your x and y on its mean, right? That gives you x bar and y bar. Then you perform SVD, and the matrices that you get from SVD, you use them to calculate the rotation. Now, one of the conditions of rotation is the determinant of rotation matrix should be equal to 1. If it's not equal to 1, you force it to 1, right? And then using the information from the mean, you calculate the translation, which is equal to n minus rm. N is mean of your x data, m is the mean of your y data. And then you use that r and t values to reduce the cost function. And you need at least minimum of 3 points to resolve for r. Now, this is a repetitive process. This process keeps on going. In ICP, either you define the number of iterations. Okay, 1,000 iterations, 100 iterations, 10 iterations, right? And as long as this cost function is less than this error, your loop will keep on going. And the other termination condition is the moment so unless this error is greater than e, this threshold e, the loop will keep on going. So the other threshold is as the moment this error becomes less than this e, the loop terminates. And you say, okay, we have found good alignment of this data now. Now this cost function is very low, right? And we have found a good correspondence between these two values. So low cost function means high correspondence, right? Now, calculation of mean is, yep.
Why does SVD give you this rotation mechanics? How do you do that?
So we have, if you remember from the previous lecture, we have some eigenvalues and eigenvector information that gives you information about the spreading out of your data along the principal axis. So SVD actually uses that information to calculate. And as we are centering our data on the mean, and with SVD we know the maximum variance along two axes, y and x. So that information is actually used to calculate the rotation along the mean position.
Okay, so you look at those axes and you see how they differ.
Exactly. Yeah, and as they are centered on the mean, you already know the mean of the data as you are subtracting mean from the data. So from that point, that's how it actually gives you your rotation on the matrix, right? So calculation of mean, SVD, rotation, all these steps are very simple. The most computationally expensive step is the computation of correspondences. And I have said, okay, if you're doing it manually, you have to click on two different images. If you're doing it automatically, you have to detect 3D key points. You have to extract feature around those 3D features around those points. So it takes you a lot of time to get to that corresponding, to find those corresponding points. Okay, so conditions of ICP. So the 2 points cloud should be close, otherwise ICP will fail. If the points clouds are far away, it would fail. So they have to be very, very close, and then you perform some iterations, and then they are registered, right? So they should be very, very close. And if they're far away, you have to give some corresponding points manually, okay? Or you can use any automatic approach, right? And then if they are not close, the first set of correspondence must be provided, which could be done manually or automatically. And ICP can still fail when the surface is rotationally symmetric. Let's say flat surface. If you're trying to register two flat surfaces, ICP would fail, right? Because getting correspondence, establishing correspondence between flat surfaces is very difficult. And the surface has repetitive structure. You have a wavy structure, let's say. In that case, ICP would also fail. Okay, then, okay, before I go to the example, I'll just quickly run that code again. So what happens when you, okay, so we have two different meshes, mesh 1 and mesh 2 here, right? You can see on the left in the workspace, we have mesh 1 and mesh 2. Mesh 1 is a 2.5D view of an object, mesh 2 is another 2.5D view of an object, right? So scanner was slightly moved and the next view was captured. So I use x1, y1, z1, x2, y2, z2 to extract the information about x1 and z axis. So this is the first 2.5D view of an object, right? And then I plot on top of that another view of 2.5D view of the same object. So it's the other view has this other view has been captured from slightly different angle. So are these views aligned? No, they're not aligned, right? So, and what's the reason for this misalignment? Either the object was rotated or the scanner was moving. So there was some rotation and translation between the two. Now, so what did we discuss? We multiply our point cloud y, or second point cloud with the rotation matrix, and then we add the translation into that, right? So I have provided rotation and translation matrices for this particular case. You don't have to worry how to calculate that, because that's beyond this unit, I would say, because there are so many computations involved in the back end. So you don't have to worry about the rotation and translation matrices. So as an example, I have provided them here for you guys. And again, this code is available on LMS. You can actually run it later on if you like. So you compute your translation rotation, and if you look at especially as here. So we are multiplying point cloud 2 with the rotation matrix, and then we are adding the translation here. Where was the rotation? And wow. So T is right here. Sorry for the resolution. T is here. So we are adding translation to the to this matrix actually. Oh, sorry. Okay. So once you multiply your point cloud 2 with your rotation matrix and add the translation, you get this sort of image. Now is it aligned compared to the first one? Yes, right? These two images have been aligned. You can say they have been registered. And at this stage, I didn't use any ICP. If you use ICP, that will actually help them to improve the registration further. All right, so that's used for fine registration. So that's just an example of how to use and how to perform these, how to establish correspondences and how to align the views. Now what happens here in ICP? Again, using the same example, you find 3 corresponding points, you calculate rotation translation matrices, you perform your registration, and you align the 2 views, right? And alignment is done the same way. I have demonstrated here in the a moment ago, right? So this is a line view of a dog image, and then if you have multiple views of an object, you align those objects by computing rotation and translation between each view to get a complete 3D model of an object, right? And then again, you can use that 3D model for any higher resolution, like high animations, for graphical stuff and all that, right? Any questions so far? Okay, now we're going good. Okay, that's good. Okay, so ICP can be used for aligning or registering 2 different surfaces, 2 different point clouds. For example, again, 2 different 2.5D views. You can register those views using ICP. You can use ICP to align a small patch with the surface, right? But of course, that patch will be a part of the surface. Right, so you can use ICP to align a small patch with the surface. You can look at these images. There are some tiny patches which have been aligned with the surface using ICP. And the final value of error is used to decide how well the 2 surfaces match, and that error we get from the cost function that we can compute, right? And so if you look at this example, so ICP can be used to align the surface and register the surfaces. If you have some tiny patches of faces given to you, and if you use ICP to align those patches with the surface, and if that is small, you can use that information for recognition as well, for face recognition, right? So if you get a very small error for one particular surface, you say, okay, this particular patch belongs to this face, and you say, okay, I have identified this image. The advantages of ICP are partial surface matching could be done, and it has inbuilt correction of alignment, and that's based on the cost function. And as we said, there are so many iterations involved. It keeps on going until that you get a value which is the error value which is less than the threshold. And the drawbacks, it is computationally expensive because there are so many iterations. You have to find the mean values, find the correspondences, find the closest points, and reduce the cost function here. So it's computationally expensive. There are few efficient implementations of ICP available now. You can find them online, but still, those efficient implementations are not that fast, I would say, and you can't use them for any real-time applications. Okay, so we have different sort of scanners which capture. While capturing data, they return you 4 different sort of matrices. First matrix contains X information, other one contains the Y information, and the third contains the Z information, and then we have an M matrix, which gives you valid and invalid points. So valid points are those which have been scanned correctly by the scanner, and as you're trying to capture depth or a 3D information, scanner sometimes misses some of the points. Right? It could not capture some of the points, so it returns you 0 for those points, right? And that's why if you look at your Kinect data, there are some holes in the data. There is some missing information in the data, and that's because of those invalid points. And Kinect 2 gives you X, Y, Z, and RGB information as well. And the images that I showed you, the serial box images, it's from the Washington data set, and they provide you X, Y, Z information and a color vector as well. And then you can use a scanner, I think scan 3 or this built-in command in MATLAB. You can use that, I think it's scan 3, scatter 3, sorry, scatter 3. You can use scatter 3 to actually plot that X, Y data and then project that color information on top of that, right? So since the point cloud is arranged on a planar grid, a simple 2D Delaunay triangulation of the XY coordinates will give you the mesh, and the Delaunay triangulation connects 3 nearest points. In MATLAB, you will find a built-in function of Delaunay triangulation, and what does it do? Let's say if you have given, you give it a mesh, it finds 3 nearest points, and then connects these 3 points. Now the problem with this triangulation is if you have a point on the border of an object, on the edge, that will be connected with the point on the top of the surface, and that will give you an elongated triangle. I have one example image, I have intentionally included that there as well. So that gives you an elongated triangles, which are, and these sort of triangles actually removed from the data because they don't carry information, right? Now, if you, I hope you guys are familiar with the peaks command in MATLAB. If you use peaks, you will get this point cloud on the left that gives you X, Y, and Z information, and then you use plot 3 to plot this data. And if you perform this Delaunay triangulation on that data, you will get this sort of mesh, right? So it connects 3 nearest neighbors to give you different sort of these different triangles, and you get the a connected mesh there in this particular case. Now, we have 2 different terminologies, depth images and range images, which is used frequently in computer vision literature, right? So these 2 terms are actually interchangeable. So sometimes people use range images for depth images, sometimes they use depth images for the range images, right? So these terms are used interchangeably in the literature, and people differentiate these 2 things based on the way the images are captured and the way they are represented. So when you talk about, so depth image is sometimes called Z image as well. Why Z image? Because Z is the 3rd dimension in the data, right? So we call it Z images, X, Y, and Z. So Z is the 3rd dimension there, so we call them Z images as well. So the depth images are just like 2D images. So 640 by 480 captured by Kinect. But instead of intensity values, what do we have in the image? depth images. So instead of intensity value, what do we have? Depth information, right? And what is depth information? What is depth? Distance of an object from, let's say, some fixed plane, distance of object from the scanner, right? So you project a light from the scanner, it hits the object, it's reflected back, and objects, you get some information about the distance, and that information is used to capture that depth data, right? And that's why we don't need a stereo vision system to calculate that depth in ambiguity, because our Kinect scanner or our 3D scanners actually already take care of that, right? So we have depth information in that case. And range images, mostly, yeah, people call it them because when you represent your data in the form of 3D point cloud or the meshes, they call it range images. But again, in the literature, these two terms are used interchangeably. People call them depth images, range images. They're the same. Okay, so Kinect 2 gives you your depth images, and then you can use that depth info. And yes, you can always convert your depth information to a point cloud and a point cloud to depth information directly. And there's a very good code available online on the Washington data set, their website. I have provided a link in what you need to know in your LMS. You can find a link there, and you'll find really good code to play with the 3D data. So you can read the point cloud, you can convert your point cloud to depth data, you can read the depth image. Reading depth image is pretty simple in MATLAB. It's just like ImRead because it's in JPEG or PNG format. And then you can use, there are some codes available to convert that depth information into a 3D point cloud information.
Sorry.
Yeah?
Did you say that Kinect automatically does calculations from like camera center to plane?
Yes, it does, yeah. Automatically, you don't have to do anything. Yes, if you are aligning the views, you'll just have to take care of the rotation and translation, right? Now, some example images that were captured using depth. So we have RGB data, and the first row is your depth image. And if you look at this, we have some really bright pixels, the nose thing, which was close to the scanner. And then as your distance increases, that brightness slowly and gradually decreases as well, right? So that's how the depth information is captured, and it's used for different image recognition and face recognition stuff, right? Just an example images. Okay, so what else can we extract from 3D images? And so with 3D images, we have surface normals as well. We can compute surface normals. So surface normal is a normal to a triangle, each triangle of the mesh, right? And then for each vertex, what do you do? You average out the surface normals of the neighboring triangles to get the information to get the surface normal at a vertex, right? And surface normals are, you can call them like in 2D images we have gradients, right? And 3D we have surface normals, right? So it's somewhat the similar thing. And then you can get the maximum minimum curvature. What is maximum minimum curvature? So maximum variation in the surface and minimum variation in the surface, right? So we have given surface, you can calculate where we have a maximum variation, where we have a minimum variation. And these curvatures are very robust. Even if you rotate the object, they don't change, because curvature stays the same. It doesn't change. Then using these curvatures, you can calculate Gaussian curvatures by just multiplying your minimum curvature with the maximum curvature. And then you can also calculate average curvatures. And these curvatures have been used a lot in different techniques for calculating the shape of the object, for analyzing the shape of the object, and for different tasks like recognition and all that. We have one example in the upcoming slides, right? Now, coming to applying 2D techniques on your Z images or your Z depth images. So if you do some triangulation using your point cloud, and if you remember, I told you guys point on the edge, on the border of, on the boundary of an object will give you an elongated triangle, right? That Delaunay triangulation gives you that triangle, and that's what you need to remove. And you have to remove these elongated triangles, okay? These are really big triangles, and you can, let's say, use technique like finding the area of a triangle. If the area is very big, you can just get rid of that triangle. And if you look at the two images, the right one is very smooth because we have done some Gaussian filtering on that. A 7 by 7 window with the sigma equal to 4 has been used here. And if you look at that, we just use normal 2D image processing technique here, that filtering technique here, and it still helps to smooth your data, right? Only problem is you miss some information as well. You have holes in the data as well, right? And there are some ways to get rid of. So if you look at here, these are some holes and some missing information. These black regions indicate that missing information, right? So, but there are some ways to fill in this information, and we'll look into that in a little while. So smoothing, you can do smoothing with a median filter. Okay, if you look at this image, you can see different spikes on the left. Some outliers are there as well. And if these outliers are there, and these are actually, you get these outliers during the scanning process, and you can't do anything about them other than doing manual processing and removing them from the image. During the acquisition process, you can't do anything. Yes, once you have that 3D image, you can always process that image to get rid of all these things. And these outliers are very problematic for in recognition tasks, in segmentation tasks, because they are part of the images and they give you some misleading information, and that's why people normally remove these spikes and these outliers from the data. And then again, if you perform median filtering, that actually helps you to fill in the missing information and gives you a slightly smooth information. Again, normal 2D data processing, you're just applying it to your 3D data. Nothing complicated, right? So the same filtering concepts. Now, just like 2D images, you can also calculate the X and Y gradient of an image, right? And if you look at this image, you can always display your X and Y gradient values. And you can combine these values. You can use these values separately for, let's say, if you're doing recognition, then of course, or you can combine all the three. So range image itself contains all the depth information. X gradient gives you the X gradient information. Y1 is giving you the Y gradient information. If you combine the three, you have three different informations for your recognition. You can fuse them. You can use them separately, and let's say you can say, and if you're doing some sort of recognition, you can say, okay, I have three matches for these three images. Okay, this image is classified. It belongs to this particular category. So this is just one example. You can extract X and Y gradients, and you can combine them with your original depth information to make it more meaningful, to make your data more meaningful. Yes, then you can, if you remember, we discussed HAR classifier in where we have a window that actually moves over an object. We have zeros and 1 pixels, and you can use that classifier on your 3D data as well. For example, people have used this classifier to find prominent facial landmarks, right? So prominent facial landmarks are your nose, tip, that never changes, corners of the eyes, even the lips, right? They find landmarks there. So let's say if you train your classifier to detect a landmark or a key point on your left eye, what will you do? So you have a trained classifier to detect a point on the left eye. What will you do for the right eye? Flip the image. You flip the image and use the same classifier, same detector, because our face is symmetrical, right? So you just flip the image and find that classifier, that landmark directly. So these classifiers have been used for finding all these landmarks of the image. And the good thing about this classifier is it works in real time. Works in real time, so it's very, very fast. Now coming back to 3D space. And to our first 3D feature. Yeah. Yeah.
So is that a 2D image that it's detecting the features on?
Yes, it is a 3D image. Depth information.
Are you able to detect like a nose in 3D space?
Yes, you can. So let's say if you're just using the height information, right? The Z information. And let me just take you to, so if you look at the nose region, it's brighter than the rest of the face, right? So you can use this. This is not actually intensity value. This is depth information, right? If you look at RGB image, it's very hard to distinguish the nose region from rest of the face. But for the depth information, this region looks very bright. You can use this information to detect the nose in your face as well. Or you can extract the nose tip, actually, which is the most prominent landmark in your face.
But isn't that still finding in 2D space?
No, it looks like a 2D image, but the information is a depth information. It's a 3D information in it. It's not a color information. So you can think of it, it looks like a 3D mesh or a 3D point cloud. Right? Okay, so coming to the first 3D feature, which is a spherical feature. So, for example, you take one reference point, let's say that nose tip is one of your reference points, and you create a sphere around that point, right? And you count the number of points that actually lie, points on the surface that lie inside that sphere, right? So let's say you say starting at a radius of 2. You compute the points. Then you slowly increase the radius of the sphere, right? And then you again find the number of points that actually fall inside that sphere. And then you again increase the sphere, and the size of the sphere, the radius of the sphere. You can again compute the points that actually lie inside the sphere. So as you change the size, the number of points would increase, right? So for each given radius, you get different number of points. So, and for different radii, let's say if you are using 3-4 different radii, you get 4 different values for the points, and that information is used as a feature in this particular, in this sphere feature case, in the case of sphere features, right? So you use sphere or different radius and accumulate all the points together, put them together, and then again these features are used for recognition, and like. And recognition is the main thing that is done using these, because you do feature matching. And then again, yeah, you can use for, if you have 2.5D views of a face from one angle, another angle, you can use that for registering the faces as well. And it's easily implemented by histogramming only the radii values in spherical coordinates. You just create one histogram of the feature values. Now, another popular technique is spin images, which was proposed by Johnson and Habert in 1999, and it is a very popular 3D feature extraction technique. So what happens, given 3D surface normal on a surface, they spin a 2D plane around that surface normal, and they accumulate the information about the surface points that is to intersect with that spinning plane, and they store that information in the bins of that plane. So you can think of, let's say, just think of, we have this object, and we have a surface normal here, and this is your spin image. You just spin it around, right? And it intersects with the object, right? So just imagine it just intersects with the object spinning here, and it captures information about the 3D information about the surface and stores them in this 2D histogram, right? And the images that you get, they are these sort of images which are computed around different surface normals, and these 2D histograms are then used for as a feature for computing correspondences between two objects to accomplish tasks like registration or recognition. and this technique achieved very good recognition results and was used as a benchmark once. Now, of course, now we have some really good techniques out there, but this one of the very good techniques. Now we have another technique which was proposed by one of the PhD students here in UWA. It was back in 2005 and 6. So what they do, instead of 1D and 2D, they compute 3D histogram. So they take this sort of grid and they project the surface inside that grid, and they compute the intersection of the surface with each cubelet in this grid, right? And that information is then used to get a 3D histogram, and they call it their 3D feature in this particular case, right? So slightly different from that spin images. So yes, just the cubelet information, all the pure 3D information in a given cube. Now a quick comparison of this 1D, 2D, and 3D. Any questions so far? Any questions? No. So a quick comparison. So spherical feature does not need any reference vector or coordinate basis, because you give it a reference point, and with respect to that reference point, you change the radius of the sphere and compute your points. And it is most robust and less descriptive. Why is most robust? It does not need any coordinate basis, any reference frame. So if you rotate the object, your reference point doesn't change, because you're using one reference point and computing your sphere on top of that point, or defining your center of the sphere on that point. So that's why it's robust. And why it's less descriptive? If you have lesser number of points, you get a different feature, right? So you have image with high resolution image and low resolution image, you'll get two different, of the same person, you'll get two different sort of features. That's why it's less descriptive, right? Now coming to spin images, it's, when it comes to robustness, it's medium robustness. It has a medium robustness and it has a medium descriptiveness. Why medium robustness? Because it relies on surface normals. And as the object is rotated, surface normals change. Surface normal change with the rotation, right? Because it's always with respect to the fixed coordinate axis. So change the surface normal also change rotation. That's why it's it's medium robust, I would say, and a medium descriptive. Now coming to the tensor feature, it is least robust. Again, it relies on surface normals and the coordinate axis. Coordinate axis is a reference frame, actually. It's called local reference frame on an object that's computed on a, that's again a totally different topic, but it's a fixed plane or fixed reference frame on an object, and as you rotate the object, your main reference frame changes. That's why your robustness is affected by that, but it is most descriptive. Why it's most descriptive? Because you're capturing the actual information of the subject, of the surface, by computing the intersection of the surface with the cubelets of the cube. And you're using that information, you're adding that information to create your 3D histogram. That's why it's more descriptive. We have more information, right? So in 1D, we have information, you add point clouds. In spin images, you put them in 2D images. In 3D, we capture the whole surface information, the surface area information, so we have more information in that case, right? Now, another type of 3D feature is shape index. Which actually relies on the minimum and maximum curvatures, and each surface is represented by a shape index. So, and the values are assigned between -1 and +1. So you have 9 different sort of shapes here, right? So each shape has its own index. So you have cup, and opposite of the cup is a cap, and then you have ridge, saddle invert, and saddle ridge, and all sort of stuff. So given a 3D surface, you compute its shape index using that particular expression, which relies on maximum minimum curvature, and the index value that you get, based on that index value, you decide the shape of the object, right? Now coming to 3D face, you can also use this shape index on a 3D face. You compute shape index at each point, right? And then you scale down the values between 0 and 1. Instead of using -1 and +1, you scale your values between 0 and 1. So this, if you look at this information, what do you see here? What is your interpretation of this data? How can we use this information, this surface, the shape index information that has been mapped on this face? For feature detection, how will you do feature detection? Yes, that's correct. So, and if you look at, and how can you do that? You have some extreme values. Let's say you have 0 as an extreme value. You can detect points here in these regions. And then you have some values more like 1. You can find the nose region, cheeks and all that stuff. So you can find some important points. Yes.
On the previous slide, you just made a mistake of H equals K1 and H equals K1.
Mm-hmm.
Is that right? It's originally 1.
That will, yes, that will actually. It won't give you 1, it will give you a value between +1 and -1. Because the shape index value, you will get a value between +1 and -1.
Yeah, but I mean the thing in the octant.
Which?
Sorry?
It'll tell you what quadrant. It should be like arctan 4, so it gives you the quadrant information.
Yeah, exactly. It's just the angle information, and then you, because these will be your principal minimum and maximum curvatures, and this tan actually gives you an angle.
Yeah.
And when you calculate that angle by, you will get a value between +1 and -1.
Isn't the thing inside the octant always going to be 1? It's H equals K1 divided by H equals K1.
No, that will change. That will change depend on the surface, right? No, it will be these are two different values that will change with the surface.
All right, yes.
These are maximum minimum curvature values, right? Not a problem. Okay, now coming to, there was a good point, a good question, by the way. I never thought about it. Okay, now coming to key point detection in 3D images. So it's similar to corner detection, similar to finding significant points on an image, right? Just the way we did it in our 2D cases, like log and blob detector in the case of SIP feature, right? It's pretty much same as that, but we do it in the 3D domain. So we need to detect interest points. And why do we need to detect interest points here or 3D key points? So if you use all the points on a 3D surface, that will be computationally expensive. If you extract feature from each and every point of a 3D surface, that will be computationally efficient. So if you just find some significant points on a 3D surface and use those points for feature extraction, that will make your algorithm computationally efficient, right? So instead of extracting features from all the points, you just detect some significant points and extract features around that point. And instead of rectangular window, you will use a circular patch in this particular case because you have a 3D surface here. And the other reason is all locations are not discriminative, right? So first you have, let's say, some prominent points and nose tip, which is discriminative. Information about that point is very discriminative because everyone has, most of the people have different noses, and then you have different information about eyes, right? So that actually helps you to reduce your computation time. And yes, this image again, it gives you some idea of getting some of the extreme values, help you to detect, give a small number of significant points instead of going through all the images, right? And in normal cases, what do we have? We have like 10,000 to 20,000 points on a surface, right? So if you reduce that computation from 20,000 points to just 100 points, that will be computationally efficient, right? Now, you can apply image-based techniques on the depth images as well. the way we did it in our 2D cases. The problem is that it does not fully exploit the potential of 3D data, right? Otherwise, 3D surfaces are smooth and corners and edges are subtle, and corner edges are at boundary and at noisy locations. So if you remember from Harris corner detector, it looks at the corner information, but the problem with 3D data is that the corners and edges in 3D case is very noisy. In the case of 3D is very noisy. So if you are using 2D techniques for feature detection, those techniques would fail. Those techniques will not give you very good feature detection points. And another problem with rotation, the pixel values change in depth images. So let's say if you're looking at an object from one angle, you slightly move, the depth information changes because you see a different view of the same object, right? The location changes, the depth information changes. Is this the case with the RGB as well? What do you think? Is this, if you look at an object from slightly different location, does the RGB information change?
Yes, the color can change because the lighting.
Let's say the lighting is same. It won't change then. Yeah, it won't change. But yeah, if you have a different lighting, yes, it would change again. Yeah, because illumination is one of the problems that we discussed. One of the challenges. Yeah, right. So if you slightly move, that depth information changes. So these are some of the challenges that you need to address. So coming to the first key point detection technique, which is pretty simple and very efficient. It was proposed by me in 2015. So given a 3D surface, you compute surface normals, we call them vector field, and then you compute the x, y, and z gradients at each point, and then you sum that gradient. So and when you sum that gradient, what do you get? Divergence. That's called divergence. And when you sum the gradient values, you get a scalar value at each point, right? And this expression itself is called divergence of the vector field. And what does divergence actually do? It measures the spreading out or convergence of the field, right? So if you look at this surface, so your vector field or surface normals are spreading here in this region, so you have very high divergence values. While you have is contracting here, you have very low divergence values, right? So we use this information to compute more discriminative key points. So we just retained the key points with the high divergence values, and we just get rid of the points with the negative or very small divergence value. So that helped us to find some sparse points. And the good thing was the points were highly repeatable, which is one of the requirements. And we got very good recognition results with all these. I have some results, and I'll share with you guys later. Okay, so these are the key points. So we use 3D mesh. We use 3D point cloud. So for 3D mesh, we use UWA dataset. We use Foscari dataset, which was proposed recently, and then the Washington dataset. So it was really good and find some really discriminant and very repeatable key points on different sort of surfaces. Okay, so with the divergence, we of course came up with the key point saliency measure to find really salient points on the surface, and this threshold T delta was used in that particular case. So a smaller value of this threshold gives you more key points, and as you increase the threshold, your key point, the number of key points reduce. That means you get more significant or more salient key points on the surface. So this threshold really, by just changing the threshold, you can actually get different number of key points depending on the task. And if you have less key points, you'll get some less discriminant features, and you can match those features in a very short time, and you can come up with some real-time application in that particular case. Okay, so let me quickly go to another type of key point detection technique, which is again very famous techniques. One of the famous techniques, and it's called key point quality. And the good thing is, in these both techniques, your unit coordinator Muhammad Banamon was the co-author. So yeah, so this one was also proposed by one of his students. So given a point P, what they do, they crop out a spherical region with radius around it. So they just take one point P on a surface and they crop a patch, a circular patch around that. And say let P be the 3 by n matrix of n points inside the sphere, right? So it's just 3D information. You call that small patch or small sphere a 3D patch, right? So you have x, y, and z at each point of that point. And then they compute the covariance matrix. And after covariance matrix, they perform PCA. But their PCA, instead of reducing the dimensionality, their aim is to align the object along the principal axis. So PCA gives you variance along your x and y directions, maximum variance along x and y direction. So they use that information to align the object along the principal axis of an object, along the principal axis. And then once they have aligned their patch with the object, they compute maximum and minimum values along x and y direction. That gives them this particular ratio. And if the value of this ratio is greater than some predefined threshold, they accept the point as their key point. Right? And if you carefully read their paper, this is basically an extension of Harris corner detector, right? So, but it has been done in 3D, and they got really good results, very highly repeatable key points. And as I've told you, they do some PCA sort of stuff. There are some lambda values. And you can think of this ratio as the ratio of the eigenvalues as well. But this one is an easy way to understand and interpret the information along the principal axis, x, y axis of thing that they use. Now again, they have a threshold, and they change that threshold to change the number of key points that they detect on each surface. And of course, if their threshold is very high, they will get lesser number of points, and as they reduce the threshold, they get more number of points on the surface. The good thing about this KPQ is you can automatically select this scale. If you remember, we discussed this scale in SIFT. SIFT comes up with automatic selection of the scale, and what is the scale? Let's say in case of SIFT, what is the scale of a key point? The size of the rectangular window or the square window. The size of the window around the key point defines your scale, right? So in the case of SIFT, it gives you the scale of the key point, right? So the area where you need to extract the feature once your feature point has been detected. So the good thing is this key point detector actually comes with this facility. It gives you a different scale, and they use different values of the radius r, and they choose. So radius is basically the size of the patch. They use different radius value 1, 2, 3, 4, 5, 6, and they compute lambda 1, this ratio lambda 1 by lambda 2, and if they get maximum value, the radius that gives them the maximum value of this ratio, they select that point as the size of the patch. And yes, of course, for different points, they get different side of sizes. And what is the significance of this scale actually? It helps you to find objects. If you have like smaller or bigger objects in the scene, it helps you to find those objects. And they have demonstrated some results there in the paper. Okay, so once you have detected your key point with KPQ, they perform some facial recognition. They use the detected key points. They form a mesh of these points, and then they use that mesh information directly, match that information to perform recognition tasks. So example of some correct matches and incorrect matches are given there, and you can see even a slight change in the mesh gives you incorrect match in that particular say. They got actually really good recognition results in this case. So similar faces will have more and especially coherent matches, and different faces will have fewer and especially incoherent matches. So similar faces will give you good matches, and you'll get a good correspondence in that case. And if you align those faces, you get good recognition results. Right? Some example from the KPQ. So they match KPQ features to find objects in cluttered scenes and unknown scale. So what they did, they detected key points on the scene, and they already know the scale of the key point, like the size of the patch, and around that patch they extracted the depth information, the 3D information. They used that depth information directly as a feature, and they matched those features. So given a 3D scene on the right and a 3D model from the library, they extract features from the scene, they extract features from the model, they match those features, and they get different correspondences. These blue lines give you different correspondences. Yes, most of the correspondences are correct. There are some incorrect correspondences as well, and the similarity measure that you use, based on those measures, you actually drop these incorrect correspondences. So you prove geometrically inconsistent matches. And once you have developed these correspondences, the next step is to, given a 3D scene, the next step is to align the object with the scene. So you have developed your correspondence, you bring that model and align it with the scene. This is done step by step. So what happens there? You align the database model with the scene, verify the match. So how do you verify the match? You compute perform ICP, and based on the error that's returned by ICP, you make a decision, okay, this object has been correctly aligned with the scene. And of course, for good recognition and segmentation of the scene, this ICP error should be very, very small, right? And the aligned model should not block visible surfaces. The aligned model should not cross over into other objects for a good alignment, right? So, any questions? How was this recognition done? The 3D scene recognition? Okay, so you have this 3D scene, right? You have this 3D scene. Just consider it as one independent 3D image. You have 3D scene. You have 1, 2, 3, 4 different objects, right? And then you have few 3D models in your object data set, right? You compute, you detect your 3D key points in the scene. You okay, what happens initially? You calculate or detect 3D points on your models, all the models, and you extract 3D features. So you can think of 3D features as depth information. You can use 3D tensor. You can use spin images. You can use any state-of-the-art technique, feature extraction technique, right? Again, with the key point, you will get a scale around the key point, and using that patch, you will extract some information. So you have features for a 3D model, right? And then you bring this scene, you detect key points, you extract the features from this scene, and then you match the scene features with the model features. So you match, let's say you take this one feature from this part of the scene, and you match that with the model features. Then you take features from this one, this one, this one, and you match with the model features. So as an example, we have just included one object here. So maximum matches are, or maximum correspondences are with this object, because you find maximum feature matches in this case, right? So let's say if you compare it with the chicken 3D model of a chicken, you will get maximum correspondences for a chicken model, right? So that's how this correspondence is established. And then once you have the correspondence, you compute the rotation, translation matrices, and you align the object with the scene. Now, again, I have provided a demo there. Code is available on your LMS. So this is a 3D scene, right? We have original scene that has 3 or 4 different objects. The chef image, we have chicken and rhino there. So this is the original image, and you compute the correspondences between those images, and you get this sort of results. So this result is again from one of my research papers, where I detected that, proposed that keypoint detector and other techniques. So you find correspondences between different objects, and you align those objects or register those objects with the scene to get a complete 3D model of so after developing correspondence, you align your the model that gets maximum score with the scene object, and then you perform ICP to refine that registration process, and you do the same for all the 4 objects to get this sort of recognition results, right? Now, quickly summarizing the 3D shape matching pipeline. So we detect key points in their scales. It's a feature detection thing that we discuss in 2D as well. Once you have key points, you extract features around that key point, around each key point. And you can think of KPQ features, spherical features, spin images, tensor, curvatures, or any other state-of-the-art 3D feature in this case. Then you perform feature matching. So you have features from a 3D model, feature from a scene, you match those features. And you can use L2 norm, you can use dot product, you can use cosine to find the similarity between the features. So if your similarity score is very high, you say we have actually recognized the right object. Then you prune some matches, remove geometrically impossible matches if a point is far away, if the 2 points are far away from each other, or their neighboring information is not matching. You just get rid of those points, and then you verify those matches using ICP. That's basically refinement, right? The correspondence refinement, and you finally output the best match. And you say, okay, this match is correct for this particular object. That's how this whole process works. Okay, so you can recognize object in a scene. You can detect object in a scene. What else? What else can we do? So you can match objects and in 3D data. So can we recognize action in a scene? Instead of recognizing a person in a scene, can you recognize action of that person in a scene? So if someone is waving, you say it's waving. Someone is punching, you say it's punching. If someone is running, you say it's running. Yes, that's possible. So action recognition is also getting a lot of popularity these days. People are working in that area. So how is it performed? You find space-time. There are techniques called space-time matching or spatio-temporal matching, which are used to recognize action. So let's think about optical flow. If you remember that motion field, we have different vectors from one frame to another frame. And action recognition is always in the video sequence. So you compute, let's say, motion field from one frame. You have different velocity vectors. That actually helps you to compute that action, to accomplish that action recognition thing. So I'll just come to that in a little while. So so 3D spatial, we have another thing called 3D spatial temporal matching. 3D means X, Y, and Z information. You captured using a 3D data. And why it's 4D now? Time. The 4 dimensions time. So you have X, Y, and Z, and then you have different frame captured at different times, right? So use that information to compute to determine the action, to recognize the action of an individual, right? Now, what is the motivation? 3D data is preferred for action recognition because it can capture all 6 degrees of freedom, 3 rotation and 3 translations, because you have X, Y, and Z information, right? More information compared to 2D. 3D avoids texture, which can cause errors in action recognition. Connect 1 and Connect 2 are available at very low cost to accomplish all that thing for you. And what does Connect 1, Connect 2 give you as an output? If you look at the images, you get these sort of skeletons. And you don't have any texture information or any other information, but just these skeleton. And Connect gives depth image and skeleton data at 30 frames per second. You need video data. You need 3D information, and you're getting that information at a frame rate of 30, which is pretty good, So if you compute optical flow from one frame to the next frame, you get pretty good information about the velocity vectors. And you can use actions in different cases. So if you look at this action, it's quite different from this one. It's quite different from this one. So all this information is used to recognize your action, looking at how that optical flow is. It's actually all based on optical flow, actually. Right? And some interesting things. Okay, action recognition is one thing, and it is done once action has been done. If someone is running, you capture that information, you come back to your lab and you process it, and you say, okay, this guy was actually running. Or you do it in real time. Let's say, okay, fine, this guy is running, this man is sitting, this person is waving. There's another thing now that people are thinking about action prediction. So before the action has been done, you just predict, okay, this guy is about to punch someone, this guy is about to kick a ball. So you predict the value before that action actually happens. Right? So people are at the moment working on action prediction. Right? So you can think of action recognition is a bit getting saturated or getting mature area, but still there's a room for research there, I would say. Now, now you can perform this, just one quick techniques for action recognition, which is histogram of depth gradients. So again, it's based on the concept of histogram of oriented gradients. We discussed Hogg. And what they do, they extract Hogg features from the depth images. So we have depth histogram, we get X gradient histogram, we get depth Y gradient histogram, and we get a temporal gradient histogram. So we have 4 different sort of histograms from the data that we compute. Z histogram, right? Gradient histogram, the next gradient histogram, Y gradient histogram, and we have temporal gradient histogram. And if you remember, we discussed how to compute that T histogram. That's the difference between one frame and the other frame, because they capture at different time intervals, right? So T and T plus 1, T plus 2, T plus 3. And then they accumulate all that histogram information to represent different sort of actions done by a given individual. And to improve the efficiency, what they do, they use a skeleton displacement feature in addition to this histogram to get better recognition results. If you're interested, you can look into the literature for more details of these techniques, because there are plenty of them out there. And like Hogg is one of the simplest technique. I think it's pretty simple to implement. So you can use MATLAB built-in codes given the 3D data if you have a video sequence and compute that to gradient information. So it's pretty simple in that. But yes, you can, there are some really good techniques, really efficient, really accurate technique out there. And for most of the techniques, even the codes, the MATLAB or a C code is also available online. Now, what is the other significance of importance of this 3D data? And you can generate a lot of training data from a single 3D image. Can you do that with a 2D image? So let's say if you have to capture 100 views of individual from with different positions of the head, and you have a 2D camera, what will you do? You'll have a photo session, right? You'll have a complete photo session, right? So 100 images. But that's not the case with 3D image. So you call someone, you capture a 3D image, just one setting of that person. He'll just visit you once. And what can you do then? You can rotate that face. You can do different sort of processing to get 3 different sort of images from this one image. So with one 3D image, you can generate a very big training data, right? So it's all your lab processing. You rotate it, you turn it, you change the color, you do this, you do that, and just one image can help you to get a lot of information. Now, concluding this lecture, so we did a bit of revision of 3D shape acquisition. We did representation of 3D data. We applied 2D image techniques on 3D data, and they worked pretty well in 3D case as well. We discussed ICP algorithm, which is used for performing fine registration for alignment of the surfaces. And in ICP, we reduce the cost function and that cost function is compared with some error threshold, and as long as that value, and the moment that cost function gets smaller than the value, ICP stops. Now we discuss some of the key point detection techniques.